So our first session is on the science of CobBauge. We spent about 5 years looking to optimize the process of combining cob and light earth. And shortly we'll hand over to the laboratory at Plymouth University to show you some of the laboratory experimentation we've been doing. But we'll begin in France with François Streff, architect and the project lead at the Parc Naturel.
Hello everyone. So I'm going to start by giving you a brief presentation of the CobBauge project and mainly the first stages of the project, so the research steps of the project. I think that you see my screen. I hope that you see my presentation. If there's a problem, do let me know. So this touches upon the various CobBauge materials that were studied within the framework of this CobBauge project. So first of all, we decided to work on soil, and we decided that we wanted to test 6 different subsoils, both British and French, so 6 in Britain and 6 in France. So here on the screen you see a grading curve that shows you the different geological origins of the soils that we studied. They're quite varied. We had soils that were mainly used in building projects with very clay-rich soils. So the green arrows here, FR3 and UK3, silty sandy soils, sandy stony soils, and silty clay soils. So very different geological soils. Once we had analyzed some of these soils, we decided to have a first batch of tests to see their performances. So we mixed these with different types of fibers. This was a way for us to, first of all, see if we could create valid samples, which corresponded to the tradespeople's knowledge. So we worked on these in tight collaboration with different tradespeople to check the plasticity of mixes, for example. And we also wanted to have a first approach to check check the validity or refute the hypotheses that we could have a mix of earth, soil, and fibers that could perform well both thermally and structurally. So these first results were discussed between different professionals in the building sector and scientists, and very quickly we realized that we had to refute this hypothesis. And we decided we would need to study 2 different mixes, one dense load-bearing mix, so traditional cob, and a light earth insulating mix, which is what we now call light earth. So the soils that we selected based on our grain or particle size analyses were 2 French soils, one that was more silty, clayey, which corresponds to classic uses of cob. For example, we see them used in Brittany, Normandy, England. And soils that were more clayey, that we then decided to keep for the light earth mixes because they had a strong cohesion strength. So the lab studies were quite extensive, and we also analyzed the different types of clay, and we realized that some of the active clay soils we'd chosen were very active or sometimes too active, and that could have led to various issues. When it comes to the fibers that we tried out, we focused on 6 different fibers, 4 different plants, and 6 different types of fibers, or 6 states of fiber, if you want. First of all, we had wheat straw as a reference point, which is quite traditional, something that is used in cob mixes. We also studied reed, which is an important resource in wetter areas in which you can work. It's an important resource, for example, in thatched roofs and recycling of fibers in both countries that took part in the study, so England and France. We also looked at hemp, both hemp straw and hemp sheaves. And we also looked at flax, which is an important production here in Normandy in France. And we looked at flax straw and again flax sheaves. So these mainly come from flax processing, the transformation of flax that aims to produce fiber. So we studied these different fibers in the labs, first of all, on their absolute density, and this could give us some clues and information as to their capacity and their mechanical strength, compressive strength. So we saw here that wheat straw gave us very weak results compared to, fairly weak results compared to the other fibers we studied. We also tested these fibers in two other aspects that we thought would be quite interesting. Their capacity of water absorption. So this could obviously have an impact on rather viscous mixes or plastic mixes like cob. So the more you have a fiber that absorbs water, the more you need water, and therefore this can make drying times longer. And there was also this question of tensile strength, which could also play a key role in these mechanical properties for the load-bearing cob especially. So we realized that the fibers that gave us the best results for water absorption were reed and flax straw. Hemp sheave, wheat straw, and flax sheaves gave a high need for water. When it came to tensile strength, very clearly, reed gave us very good results, and flax straw also. Wheat straw, which is traditionally used, gave us a tensile strength that was very, very weak. So we then, from there, decided to work on implementing different tests, different preparations of samples, especially for the thermal layer. We created these blocks, and then we put these through different testing machines to determine their thermal resistance using heat flow sensors that you can see in the pictures here. So different mixes that were then tested using these methods. Obviously, using 4 different soils that we kept and 6 different fibers, we then had many possibilities, different samples. And so here we focused on what's on the screen, so an experimentation plan that allowed us to try out only some of these mixes, and then this meant we could extrapolate the results from the ones that we tried out. So here the experimentation plan for the mixes, for denser mixes, which we could consider the traditional cob. So here you can see some of the results highlighted. And you've got some mixes using flax straw or hemp straw that gave us a compressive resistance strength that were quite positive, so close or above 1 megapascal for a concentration of 2%. So these results were quite interesting, whereas wheat straw or reed straw, which was interesting theoretically, but in the mix with some soil gave us weak results compared to hemp and flax straw. We then did the same thing for the thermal mixes so these light earth mixes. And here we use different fibers. We focused on hemp, shiv, and reed, and used different proportions. So we tried out with a 25% or 50% in weight compared to the weight in soil, the dry soil. And we focused on two different hydric states with their water content, either viscous or more liquid, compared to what was planned initially. So in the end, we abandoned this viscous state and just did one test, but it was not very relevant for the light earth mix, scientifically speaking. We studied it, but that didn't use it. So these different samples of light earth were then tested in terms of compressive strength to see their capacity at load bearing themselves. So to see if they could take some load, some weight, and we tested these especially on the thermal insulation side of things. So here you can see the results on this graph. So you've got the different samples, mostly at the bottom left here, where you've got insulating mixes. So here you can see that you've got all the different samples that we tried out. You've got a thermal conductivity that goes between 0.1 and 0.2, depending on the density variation. So this curve shows us this relationship, really, that exists between conductivity and thermal conductivity especially, and density. So these have already been studied in the past, so it wasn't anything groundbreaking here. But these different curves and graphs helped us simulate the thermal behavior of a composite wall. So we thought about the relationship and the performance that we could get with these combination of mixes, so a thicker and load-bearing cob and light earth. So different thicknesses. So here we had two mixes that were combined. So a load-bearing dense cob mix of a density of 1.4 and the light earth mix of a density of 340 kilograms per cubic meter. And both of these were 300 millimeters wide. And we got a U value of 0.26, which means for our English friends that they comply with regulations, thermal regulations per element, because there's a limit for walls of a U value of 0.3, so we remain below this value in this limit using this process, this combination of two mixes. So this means that you can comply with regulations. So this was quite positive and significant for the future and the use of this combination of elements even in France. We also wondered what would happen with a monolithic wall of a medium density between cob and light earth that we mentioned. So if we had a light cob to get an average density of 900 kilograms, we realized that with the same thickness of 60 centimeters, the U value was much higher, of 0.41, and this means we weren't complying with thermal regulations, especially in England, and this would have meant that it was also harder to use in France. So this graph here shows you the relationship between thermal resistance and thermal conductivity. It's not a linear relationship. So you've got materials with a low thermal conductivity. If you see on the left here, you've got a reduction of so for materials with a weak thermal conductivity, you've got higher thermal resistance. So this relationship obviously touches upon all the different insulating materials, but especially the ones that were used in the CobBauge project, where the quantity of fiber has an impact on the mix's performances. So this means that when we work on modifying the different fiber content, and we tried out these things on the light earth here, if you change the density, you see that there's a large impact. There's a weak variation, so there's a high difference in the U-val. Sorry, if you look at the cob, and so a change of the cob, so if you change the fiber content, so you multiply it by 2, you go from 2 to 5%, you realize that when you increase this fiber content in the cob, the impact on the thermal resistance is minimal. So if we decided to use only one mix and use this hypothesis, a mix that would be optimum, would have like the same thickness of what we tried out previously. So here we've got a 55 centimeter wall. You could, to get a U value that was equivalent to the one we'd had previously, to have 0.26, we would need a cob mix that would have a density of 548 kilograms per cubic meter. And this means that then we would have a resistance to a compressive strength that would be 0.2 megapascals, and therefore would not be strong enough and would not be a load-bearing mix. So here, these different results that I'm showing you or telling you about, this proves that what we intuitively thought during the first tests, thinking, oh, we couldn't do one wall that would be one wall with one mix that would have the capacity to be load-bearing and insulating. Here we have a clear confirmation of that using scientific studies. So we've proven this, and so this justified why we then decided to work with a composite wall. So in addition to these different works that were carried out by the different labs who have participated in the CobBauge project, we quickly worked with other professionals and decided to work on this implementation of two mixtures that had different densities, and we tried to see how we could quickly and efficiently build a combined wall. So here you've got some of the first initial tests that we carried out, and that eventually led to what you will be seeing today in our training day. So I think I'm gonna leave it here for my presentation of the different materials and the CobBauge materials in particular that were studied. I think I'm now going to give the floor to Jim, who is going to give us a little live session in the labs of Plymouth University.
Hello everyone. What I'm going to do very briefly is to recap some of the information that Francois told us earlier about the beginnings of this project. So we started off with the idea of optimizing cob construction in order that it complies with the building regulations both here and in France. So to do that, we took a range of different soils, 6 from the United Kingdom, 6 from France. We chose 6 different fibers, and we made a matrix in order to test combinations of soils and fibers in order to discover the optimized mixes. We also realized that it was going to be very difficult to make one single material that would be both structurally strong enough and also thermally efficient enough So we looked at creating a lightweight mix, which was made out of slip and hemp shiv, and then a structural mix, which was tested for its load-bearing capabilities. We used different machines and different testing procedures in order to establish the thermal performance of the different mixes. And we also involved other techniques like thermography in order to help establish these facts. So I'm now going to hand you over to Matthew Fox, Dr. Fox, who is going to take you through some of the materials that we analysed during this process.
Okay, hi everyone, and welcome to this table of material samples. I won't go through all these different bits and pieces, but like Jim, I'm just going to quickly recap on some of the science that Francois spoke about earlier. As Jim was saying, when we started out this project, the main premise was to try and find a material that would meet the building regulations. So what we have here, this cylinder, is traditional common cob you would find in historic cob buildings. This currently doesn't comply with the regulations. We were then looking at optimizing the earth, and we then started to look at light earth construction. It's sort of very low density earth mix, which Kevin will show you how to mix that in a minute. But we were starting to look at that. Unfortunately, this is just not structurally capable of supporting a roof or walls or floors or things like that. So it's just not good enough in a structural sense, but it gives good thermal properties. So we were then thinking, well, could you have a mixture or a combination of this mixture with structural cob and kind of an in-between? We found that when you had these two materials mixed together into one monolithic wall, it no longer gave you the thermal performance or the structural performance. So it didn't work as a kind of a material product. So then we started looking at other avenues, and we came up with this material here, which is the CobBauge composite, and that's the material that we've been working with today. Where you've got on the one side, to use this one here, we have on the one side we have a structural layer, and on the other side we have a thermal layer. These, of course, are very small samples, but in the laboratory here we have a 1-to-1 scale mock-up of the wall. So we have our structural layer here, our thermal layer here, and these walls have got a particular purpose. So, Jim, would you like to explain the rationale behind these walls?
Yeah, thank you, Matthew. So these were very useful because this is the stepping stone between laboratory experiments and building an actual building. So this is a full-scale CobBauge wall. It represents the height of a single story of CobBauge. And if John swings around, you'll see that there is another wall over there, which is the same height. So that enabled us to put a ceiling across between the two walls, which has since been taken down, and we could apply the loads of a typical 2-story building. So we've actually functionally tested the material before anything is built with it. We were able to take lots of measurements. These little targets here work with a Leica 3D Disco, a laser surveying machine that records to within a millimeter any movement. So when we applied the load, which was just under 12 tons, we could see whether the walls had deflected at all. And the short answer is there was virtually no movement at all. So we were now confident that within the confines of a laboratory, we proved the concept of the CobBauge wall. So I think what would be interesting now to take us forward to the relationship between those laboratory tests and what might happen on an actual CobBauge building site. So two of the things we need to establish is how effective is the thermal mix going to be and how consistent should the structural mix be. And I'm going to hand over to Kevin Owen, our chief technician, who is going to demonstrate the practical tests which are undertaken on a CobBauge building site.
Well, thank you very much, Jim. As you can see on this table, there are various samples. There's our thermal mix, and there's the heavier, much heavier traditional cob mix there. When you're on site, you've got to come up with a way of keeping the continuity and the quality control. So part of the project was to come up with some very simple on-site ways we could do that so that the people on site who are mixing the material and are laying the material would be able to keep the same quality throughout the build. And we came up with a couple of really simple on-site tests. One we call the ball or drop test, where we drop a quantity of fiber mixed cob at a given height, and then we measure the diameter of the splat on the floor. And the second one is we call a puddle test, where we pour a quantity of the slip material from a given height, and then again we measure that diameter. And I should demonstrate those. We're working with a cob that was mixed some while ago. It's already got fibre in it. It was actually the same material that we built these walls with. And you might be able to see the sort of fibre still in it there. It's kind of gone very fibrous, but it's still workable. And what we do for the ball test is we fill a 2-litre container with this material, press it well down, reminiscent of when you're a child, you're just making a sandcastle. We're going to fill this with the material, press it well in to the top of the container. And as you can see, it's well and truly in the vessel there. Tip it upside down and knock out. Yep. And there's my sandcastle. And what we do is we pat it into a circular. It looks a little bit like a cannonball, even all the way around. So this is a 2-litre container, and we put inside there the cob mix that's already got the fibre in it. So we already know what the mixture is for that, and in this case it's a 2.5% fibre mixed with the weight of dry material. So here I've got a stick with a 1 metre mark on it. So if I drop this now from that height and let it hit the floor, we end up with a nice round splat. And all we need to do on site is just to measure that diameter. And we're looking for up to 21 centimetres. That will give an optimum mix. This one is just bordering on 20 centimetres, so that would be fine. It is possible to kind of add a little bit more material or water to stabilise that. And certainly if you've got a very wet mix, you can just let it dry out for a while and then remeasure it. So that was the ball test. Now we come to the other test we have, which is the puddle test, or viscosity test. And again, it's a very simple method. And the guys on site, when they were building our building, meticulously measured this every day. So they'd make a mix up the night before, and then they come back and then they check that the viscosity had not changed. And to do this, all you need is a plastic cup with a little mark on it at 100 millilitres rather, and a little frame here that I've got on a piece of glass with a little peg sticking out there, and that is 100 millimetres, so 100 and 100. And then down here we've got some of our slip. The slip is high clay content, so which is a local clay, not too far away from Plymouth. Very high clay content, and just add water. So you keep adding water to that and mixing it until you get to a fairly thick consistency. So you get to the point where you can take a measurement. Now what I do is I tip some of this into the cup, to the line that I've got. that. And then simply tip it over the peg. And what we found was that if we measured this, we'd be looking for a diameter of 14 centimeters. So if I lay this across there now, we're almost at 14. This material's probably dried out overnight a little bit, so I could add a little bit more water on there. But provided that was at 14, we know that it's exactly right. And all we then need to do is to add our thermal insulative material, which is the hemp shiv. And that is by weight is 50% of the dry weight of that material. Now, if you're on site, you're not going to be weighing things. You want to know what the volume is. How many bucketsfuls or tubfuls does it take? So we've calculated that the right mix would be 3 buckets or containers of the shiv. So by volume, that's 3 and 1 of the slip. Now, what we did on site was we used a vertical mixer like this one. And this actually was used for all our testing and for the building itself. So it's quite a robust machine. It's still working perfectly. I've already put 2 buckets of the material, the shiv, in there. This is my final bucket to go in. And we can start to rotate that. And without pouring it all over myself and John, add in the slip. That will now mix for a few minutes. It's a fairly quick process where the slip is being absorbed by the shiv. To start with, it looks kind of very shiny, and then after a few minutes, it goes dull, and it's at that point that we know that it's fully mixed. As you can see there, it's changing colour from that light colour to a more redder, darker. And we usually would leave that to mix for, say, 10 minutes, 5-10 minutes, until it's fully mixed up. And then it's ready to use. So when you're on site and you've got someone that's filling up the buckets or containers with material, someone mixing and then someone carrying it away, it's a very efficient and quick way of getting this material. So I hope that demonstrates a couple of very simple on-site techniques. Thank you, Kevin. I'm going to turn the machine off.
Okay. So that concludes our short visit to the laboratories here at Plymouth University, where we've looked at the relationship between the science, the early stage testing, and then the process of converting that into a system which will work on site. And everything that we've shown you here is covered in more detail in the training videos, which Tom is going to tell you about shortly.